Hi, so today we are going to talk about Michaelis Menten equation. What does this equation do? It's an equation, so it's a mathematical representation of what? Of the rate of enzymatic reactions. Okay, so how does an enzyme react? Let's see. Suppose we have an enzyme, it binds to the substrate and forms the enzyme substrate complex with a rate constant of K1, and this substrate can also dissociate and form the substrate and enzyme back with a rate constant of K minus 1. This complex can also with a rate constant of K2 form the product. We need this part of the enzyme substrate reaction to happen. So as you can see, the amount of enzyme at the end of the reaction is same as the amount of enzyme that was in the beginning of it. So this is a catalytic reaction, and before diving deep into the derivation part, I will just take a small digression and talk a bit about steady state approximation. It's a very important tool in chemical kinetics, and if I am not wrong, it was Briggs and Halden who used this concept for the derivation of enzymatic reactions. So what is this? I will draw a graph. So let's draw a nice graph like this, and okay, I will draw the arrows. Okay, and the x-axis is time and the y-axis is concentration. I will change my pen color a bit for easy understanding. Suppose the concentration of substrate was somewhere here at the beginning of the reaction, and common sense says that the amount of product should be 0 because the enzymatic reaction hasn't started yet, and the amount of enzyme or the total enzyme at the beginning of the reaction was this, and I will just extrapolate this point throughout all time. So as I mentioned before, what happens when an enzyme reacts with the substrate? The enzyme substrate complex will form, so it will go like this. This is the enzyme substrate complex, the concentration of it. What happens next is the product concentration will also go up, and what will happen is the substrate concentration will come down, and though not extremely important for us right now, but the concentration of free enzyme will decrease. So as time passes, what will happen is the concentration of enzyme substrate complex will reach this plateau. Why? Because the amount of enzyme substrate complex inside the reaction mixture can never go beyond the total number of enzymes, right? And apart from that, you can guess what will happen. The product will increase and the substrate will decrease, and the amount of free enzyme will go down as well. Alright, now what we need from this graph is basically this plateau region. Why? I will tell you. So this is the plateau. So the enzyme substrate complex forms a plateau, which means that the concentration of the complex is not changing over time. So this is inside this plateau region. Okay, in terms of chemistry, we can write this down as the rate of formation of ES is equal to the rate of dissociation of ES, right? Because the amount of complex that is being formed is the amount that is getting dissociated, maybe into product or back into substrate. Now, thanks to Newton and Leibniz for their calculus, we can write this thing in terms of calculus as the rate of change in the concentration of enzyme substrate over time is 0 inside this plateau region. So this is the steady state assumption. It's extremely easy. Now we will try to understand why did we do this and how it would help us in deriving the Michaelis Menten equation. So I will write down the enzymatic reaction again. So there was enzyme binds to the substrate with a rate constant of K1, forms the enzyme substrate complex, which might dissociate back into substrate and enzyme with a rate constant of K-1, or with a rate constant of K2 it can form the product. So when we tell that it is the rate of the equation is basically the rate of change in the concentration of product over time, and this is K2 into ES. So in this equation we want to know this, and this can be found out in chemical labs, and we don't know this. So how can we use this equation? We can write down the rate of change in the concentration of enzyme substrate complex over time as the rate of formation of the complex, the rate of formation of the complex minus the rate of dissociation of the complex to form the substrate minus the rate of dissociation of the substrate to form the product. So this part here is basically from this portion, and this part is from this portion, okay, and this part is this. So this is adding to the amount of enzyme substrate complex, this is reducing, and this is also reducing the concentration of it. So now at any particular point, what we don't know is the amount of free enzyme inside the reaction mixture that can form this enzyme substrate complex, but what we know is the total amount of enzyme in the beginning of the reaction. So we can use that and write this free enzyme thing as the concentration of total enzyme, or the enzyme that was at time 0, minus the enzyme that is already being bound to the substrate, and we will write down the equation, the other parts of the equation as it is. Okay, now how can we write this further? We will just remove all the brackets and multiply this thing like this, and we can actually do one more step here, and we can take ES out of these three terms because all of them has it, and we can write it down as K1 into substrate concentration plus K minus 1 plus K2. Okay, and now here comes the steady state approximation. From the steady state approximation, we know that the rate of change in the concentration of the complex is equal to 0 in steady state. Now, what we derived here was basically the rate of change in the concentration of enzyme substrate complex. So, we can write this down as is equal to K1 E naught S minus ES into K1S plus K minus 1 plus K2, right? And this is equal to 0. Or we can take the ES to the other side of the equation and write ES is equal to K1 into E naught S by K1S plus K minus 1 plus K2. Now, we knew that the rate of change in the concentration of product or rate of formation of product is equal to K2 into ES. We derived ES here, we will just put this down. So this equation becomes K1 K2 into E naught S by K1 S plus K minus 1 plus K2, right? Now we will divide the numerator and the denominator by K1, which gives us K2 into E naught into S divided by S plus, we'll put a bracket here, K minus 1 plus K2 divided by K1. This thing over here, this particular term is known as Km, which is basically called the Michaelis constant for a particular reaction. So this is not same for all reactions, as you might imagine, because K1, K minus 1, K2 are different, but it is a constant for a particular reaction. So what we get here is V, or the rate, is equal to, we'll just put this down and change this to Km. So K2 into E naught into S divided by S plus Km. Now suppose there is no complex formation, nothing, the enzyme just forms the product, so that would be the maximum rate of the equation. So we can write it down as K2 into E naught as V max into S divided by Km plus S. So I think you got to understand, right, why this K2 into E naught is equivalent to V max. Okay, and this is the rate. So this is in front of you, what you can see is the famous Michaelis Menten equation. Now what we can do from this equation, we can try to find out what Km is. Okay, before that I will just draw another graph and show you, if we plot this kind of equation, how does it look like. So if this is the x-axis, we have the substrate concentration, and in the y-axis we have rate. This thing goes like this, and this plateau region, what we can get, this thing is V max. Now coming back, so suppose the rate of the reaction, rate of the enzymatic reaction, or V equal to half of V max, so V max by 2. Then how does it behave? So we can write V max by 2 is equal to V max into S divided by Km plus S. This cancels out, and what we find is Km is equal to S. So suppose this is half of V max, this thing over here is Km. So it is the concentration of the substrate in which the rate of the reaction is equal to half of the maximum rate. Now when we are doing experiments, this kind of equations are very difficult to plot because we don't know at what substrate concentration we will reach this plateau. So thanks to Lineweaver and Burke, who used this wonderful equation, this Michaelis Menten equation, and derived a linear plot out of it. So how did he do it? We know V equal to V max into substrate concentration divided by Km plus substrate concentration. We will just take a reciprocal, or 1 by V is equal to Km plus S divided by V max and multiplied by S is equal to 1 by V max plus Km by V max into 1 by S. This is the Lineweaver-Burke equation that we can easily use to identify Vmax, Km, etc. Okay, we can draw a graph right now, and like this, I think it's fine. Yeah, so in the x-axis we have 1 by substrate concentration, in the y-axis we have the 1 by rate. These are the two elements, so this is y and this is x. So when S, or 1 by S, is equal to 0, so when 1 by S is equal to 0, then V equal to Vmax, right? Or I would say 1 by V is equal to 1 by Vmax from this equation. So suppose this is somewhere here, so this is 1 by Vmax. Okay, now 2, when 1 by V is equal to 0, we have, so this portion of the equation is 0, so we have 1 by S is equal to 1 by S is equal to minus 1 by Km from this equation. Okay, so this is here minus 1 by Km, and so we got the two intercepts, and this is, or I will draw it in a better way, so and this is, oh no, extremely sorry for this, and this we have the equation and the linear, and the slope is Km by Vmax. So if we have a few plots in this kind of graph, we can get Km, Vmax and everything else. And this ends our topic on Michaelis Menten equation. Thank you so much. Please like, share and subscribe, and see you in the next video.